Just a second, one curve more. Square root of G. Apparent resistivity, electrical field. Just a second, what else? Again, electrical field. Oh, now I am in good shape. So, why this phenomenon is called electrostatic, static effect, not electrostatic, static effect. Very simple. Since all part of the curve, you see, shifted in parallel, because electrical field at this place, which we measure and which creates these charges, behave in the same manner. So relative contribution remains the same regardless of period. That's the reason why it's called static effect. Then it's not necessary to have horse. Suppose we have a swamp or simply zone where different behave. As I mentioned, for example, it's volcanic cover. There is some unknown zone with low resistivity. It's shallow, it's small, it does not have any interest from geological point of view. But it will create very strong shift of the change of the field, shift of apparent resistivity curves, and creates problem. Now, it's not literally few words about mathematics. All these pictures is not a result of imagination. No. They were obtained using solution of integral equation of Redgolm of second order with first of all boundary value problem was formulated, then very complicated calculations were performed in a complicated computer, not simple computers, very advanced, and this result were very important to see real life, what sometimes happens. Now, let me, in order to accomplish this discussion, to consider one more case. In this case, electrical field is perpendicular to the boundary. But let us assume for a moment we again have the same layered medium, rho 1 H1, rho 2 H2, and rho 3 very small, rho 2 is very large, very great with respect to rho 1, rho 3. We have to have this curve. But now let us assume we have again horse, not necessarily from the beginning to end. It could be this horse. But now electrical field will be directed along strike, because we don't know how it could sometimes happen one way, sometimes another way. So let us assume for simplicity we have again the same horse, and we again measure here. So now electrical field goes in this direction, magnetic field goes in this direction. Now I am sitting in this point and measure impedance as function of period, convert with apparent resistivity, and instead of this curve, apparent resistivity, I will get completely different curve. So far, shape of the curve was not distorted. Now, I will explain you what would happen. Square root of period, apparent resistivity, in other words, field. Why, first of all, we will have secondary field? Why we will have distortion? Very simple. Now, electrical field goes in this direction. Therefore, currents which arise here along of strike will be different with respect to currents when medium was uniform. If it's a less conductive, more resistive conductor, less conductive, we will have smaller currents. When we have vice versa, opposite. So we will have anomaly. And what would happen? Very peculiar picture, very. When frequency is very high, you don't see these edges. You are sitting on the surface of uniform half space with resistivity ρ1. Then, when frequency period becomes bigger, frequency low, you start to feel more conductive medium. Which? Not which beneath, but from left and right side. An apparent resistivity curve will show you minimum, because this medium is more conducting than resistive host. Now, so what happens? You think you perform vertical soundings, but instead of it you will perform lateral soundings. Then, with increase of period, finally you start to feel resistive flare. And then apparent resistivity curve up and then down when you have this conductor. Now, what does it mean? When you look in this curve, you think I have one layer, then I have another layer which is more conductive. Then again resistive layer and then conductive. So you invented layer which does not exist. There is inhomogeneity high resistance. But if you start to interpret, you will say in the depth few kilometers I have excellent conductor. As what Duncan McNeill wanted to emphasize, interested all about gold. So this is at least numerous infinite number of inhomogeneities, infinite number of possible distortions, and finally it was realized no way to use in general except favorable conditions when we don't have lateral inhomogeneities series. We cannot use empty. When we don't have, we can use it for reconnaissance. So let me stop here as illustration of galvanic effect. Now, I would like to discuss with you one question which does not have direct relation to electrical methods. You have questions? No? No.
Has that been used for that extra layer? If you were to do a profile,
so
you would actually see the lateral inhomogeneities as soon as you start to see an extra layer.
But you will see layer not infinitely long.
Yes, that's right.
But you will see some inhomogeneity with finite dimension. That's what we see in control source MT, what we see in who knows, everywhere where we don't think what could cause it. Sometimes we do have it, then we are winners, but But we have to know where we are winners, where we are inventors.
No, sometimes we want to find that lateral inhomogeneity.
Yes, but we don't know where is it. Because when you start to interpret this curve, you will tell inhomogeneity on the depth 2-3 kilometers. Because it manifests itself not at very short periods, but very long, relatively long periods. So formal interpretation based on model of horizontal layer medium tells you there is a layer and this area on the depth 3-4 kilometers. Beyond this area, no layers. So what you are doing, you comparing results of measurements at different points. I follow you, correct? You say on the depth of 3-4 kilometers I have very good conductor, 1 ohmmeters. I have upper layer, I have another layer, here I have a zone. We would like it, but it's not real. It's caused by what? Where? Near the surface. That's the point.
That's what I'm looking for in my work.
But you are looking, but MT looking for deep tar.
Then you come back later and find out where it is. Close to where,
Sorry. I think I'm in trouble. So let us return back to this method. So we perform magnetotelluric soundings. For example, for this case, we have inhomogeneity. So what would happen far away from this horse? We will get normal geoelectrical section. First layer, second, third layer. Correct? Goal of magnetotelluric soundings to get information about second, third layer for this model. Now we perform sounding at different points. We find this layer. Magnetotelluric method is not interested by this horse on the top. It's interested somewhere on the depth. That's what we detected. But it does not exist. That's all.
I was thinking that we could use it for finding lateral inhomogeneities as well.
Oh, if, so let us forget about this.
Geoelectric section, right? I'm not interested in
Yes, you are interested in the upper part.
Yes.
So let us do Schlumberger profiling or control source MT or any electrical methods. But don't let us not measure magnetic field. Let us measure electrical field. It then be very well detected. But that's different method, different purposes. Do we, sorry.
Yeah.
Now, let me discuss with you one subject. Let me share with you my experience working with graduate students and undergraduate, both of them. Tells me it's useful to discuss one subject which has relation to all geophysical methods. We perform interpretation. Interpretation is the solution of inverse problem. Correct? Inverse problem. We have no field, we would like to find our parameters of our section. There are three concepts, or four. Unique problem, non-unique problem. Ill-posed, well-posed. So it's not too bad without mathematics understand what is behind of it. Let me perform some small experiment with you. Let us forget about electromagnetics, vortex, galvanic, Maxwell equation, go to basic, the simplest method, gravitational method. I have salt dome or any body. Can we calculate gravitational field? We can. There is a simple formula. which directly follows from Newton's law. Density, LQP, LQP cube, dV, nothing else. So, if it's a point P, it's point Q, divide volume in many elements, take elementary volume, calculate this integral, don't pay attention to this noise, there is a constant gravitational, and gravitational field is calculated. This problem is the forward problem. Let me ask you a question. How, if I change a little, how many fields create this mass? That's mass. No more charges, no more currents. How many fields at this point creates this body? Huh? One. Not two. One. So it's unique. One body at each point creates one field. Now, I would like to ask you a question. If I little change this body, took away piece, what happens with this field? Please imagine we measure exactly, we calculate exactly. Exactly. What does it mean exactly? It means with any digits after comma we know number. So again, my question, what happens with field? Changes. We are not worried where it changes. It changes because we know exactly field. So common sense tells us. If I have profile of gravitational field, everything what I'm saying apply to apparent resistivity, curves, magnetic, seismic, it's the same. Only example is simple. So if I start to change, then I will get new curve. So, if you think in these terms, you have to say yourself, each mass creates own field. Now I would like to ask you a question. Is solution of inverse problem, after this small comment, is unique or not unique? Question is, I know exactly gravitational field. How many bodies do create exactly the same gravitational field? Sorry? Infinite numbers. So you say solution of inverse problem is not unique. That's correct? It's a little strange. Only a few minutes ago, few seconds ago, we came to conclusion, cut a little here, and you will get new field. It looks like common sense tells us if each body, each shape, each density creates only one field, it should be vice versa the same. But you say no. Now, so is it possible to say that solution of inverse problem in gravity is not unique? Did you take classes in gravity? Also non-unique. So now, great. Now, let us imagine you are not students, you have small company which performs gravity service. You came to your client, West Mining, he told, I will perform gravity service. So you wrote contract down, wrote how many profiles you will make, which equipment you will do. So you went to the field, perform measurements, brought to your client report. He accepted report because many beautiful pictures you made. So, moreover, client pay you. So you took this check in the pocket, then slowly started to move from desk of client to the door. Then when you reached the door, you turned 180 degrees, he told client, thank you very much for check, but don't forget, solution of inverse problem in gravity is not unique. So there could be infinite number of answers. He then very quickly moved forward and closed the door and with high speed ran away. So I don't think that's a good situation for geophysics if each time we bravely, without thinking, say solution of inverse problem, non-unique, so thousand solutions. So situation is much more complicated. And let me tell you, if you start to think about this experiment, it's not so, at least for me, it's not so simple to swallow the concept of that solution of inverse problem is not unique. I would prefer to think it's unique. Because you little change, new field, little change, new field. So then you, at least you, I wish to say, perhaps an opposite is unique. And what it turns out, mathematicians did prove that for the most important cases in gravity, then I will tell about electromagnetic, solution of inverse problem is unique. They did because to save us, in order not create this scenario which I described so vividly a few minutes ago between client, check, door, and etc. So in effect, it's unique for special types of the bodies. These bodies are, and exactly these bodies we use in order to perform interpretation. Prisms. Prism in gravity, then I will jump to others. In gravity, if you have a prism, but let us take that's prism. And mathematician proved, to your great surprise, that if you do have prism, you don't know dimension, even you don't know density. But if you measure exactly field, exactly, mathematicians don't know what does it mean not exactly when they prove theorems. We are not talking applied mathematics. We are talking about theorems. All theorems are proved for when you assume you do know exactly your field. If they proved within class of prisms, we deal only with prisms, only with prisms. Different many sides, dimension. There is only, if you perform interpretation, you will get only one prism, this prism. Now they went further, they proved system body which consists of system of prisms. Situation will be the same. Solution of inverse problem is unique. That's what usually we are doing, performing interpretation in gravity, magnetic. We replace our model, system of prisms. Now, for example, back to this prism. Even I measured somewhere here. Oh, let me show you. It's characterized by width, one width, another width, depth, density. I measure here. Intuition tells us mainly field depends on this parameter, on density, on width, but hardly bottom. However, don't forget, you measure with absolute accuracy. Concept of uniqueness is tightly related with assumption field is known exactly. Even if you measure on the moon, but this small prism here, to your great you have to say what is the difference between this and this distance. No way to separate. You will separate. So that was great contribution of mathematicians. Then mathematicians proved if you have another type of the body, it's called star type of the body. Sphere, excellent example of star of the body. It means from any point you can draw a line, intersect surface once. Again, solution of inverse problem is unique, only with small difference. In this case, you must know density, as in the case of sphere. So, opposite what you think, some of you think, since we are working mainly with prism, system of prism, we do know solution of inverse problem is unique. The same situation in magnetic, the same situation in seismic, the same situation in electromagnetics. For example, if you have horizontal layer medium, solution of inverse problem is unique if you have measurements short, long distances. However, my suggestion to forget uniqueness, non-uniqueness at all. Why? Very simple. We never measure exactly. We always measure with finite error. So when you plot your graph, in effect, graph of the field, gravitational field, apparent resistivity, you don't have line. You have a strip. In your data somewhere here. So my suggestion, when you have your curve, it's not any, when you, no, everything is okay. So we plot graph, but instead there is no graph, because each value, for example, in gravity, 1 milligal, it's not 1 milligal. It's 1 milligal and maybe plus minus 5%. Correct? In apparent resistivity, you plot your graph. You don't have 10 ohms. You have 10 ohms plus minus 10%. So either 9 ohms or 11 ohms. So my suggestion as geophysicist, it's not too bad to understand when you plot your graph, in effect you plot strip. And your value somewhere between. At different points, width of the strip is different. So we can, if we are realistic, we have to say, for example, with accuracy 5% we define quantities which we measure. So therefore, all discussion, uniqueness, non-uniqueness, are irrelevant. They don't have any relation to our practice. Because all theorems of uniqueness are proved for assuming that we know number exactly. So we are completely in different world, in a completely different planet. And then, completely different story. Is it interesting for you? Good. It has a relation to all methods without any exceptions.
Often, very only measure a scalar.
Sorry?
We very often we don't measure a field, we measure a scalar magnitude of it.
You don't measure field?
Or like in magnetics, we take a total field sort of thing.
Of course.
And you don't know where it's going.
What we do know?
We know the scalar magnitude of it. We don't know the orientation of the field.
Oh, scalar. You mean scalar field? It doesn't matter. Yes, it doesn't. When I say field, I mean component of the field. You cannot all these discussions. Everybody understands. Electrical measure what? Voltage, horizontal component. We don't care about vertical. In gravity, we measure vertical component of the field. So we treat it as scalar. It's a completely the same, no difference. For example, in seismic, we measure time of arrival. In magnetics, we measure vertical or horizontal, doesn't matter, or both. In electrical methods, either we measure voltage or vertical component of magnetic field, doesn't matter. As soon as at all points you have the same component, that's it. Did I remove this, or you still feel? Field does not mean vector. When I say the field, I mean one of components of the field. Gravitational, it means vertical component gravitational field, vertical component magnetic field, horizontal component electrical field, time of arrival, doesn't matter at all. Now, so first of all, my suggestion, forget about uniqueness, non-uniqueness. I don't advise to tell, for example, to speak unique or non-unique problem. It's beyond of our realm, beyond of area of our activity. There is something else. Back to our prism. It's very unpleasant prism. I don't know. It doesn't. It's something. Everything except prism. Now, whether it's unique or not unique, it's not important. Even its unique solution inverse problem. Because our measurements contains error. So, what we start in general to do? We start from the first approximation, first guess, which you usually where we usually use our knowledge of geology when we have. So we take some parameters, H1, H2, D1, D2, density 1, 2, 3, 4, 5 parameters. We substitute it in this equation, correct? We perform calculation. Suppose our result is, that's our first guess. What we have to do, that's first scenario. What do you think? What we have to do next? Since you know solution of an inverse problem, you have to tell me what we have to do next. Huh? Better. So we don't like it. Why we don't like it? Because width of the strip, range of change of which characterizes our error, much smaller than difference between experimental curve and solution of forward problem. Correct? So let us improve. Step number 2. We did it. And now I would suppose we obtain our, we change our parameters, H11, H21, D11, D21, sigma density 1. And for these parameters we obtain curves which is sitting inside of our strip. Tell me please what we have to do next. Huh? What does it mean?
Putting some geological information.
No, we put before. We made first approximation. So using geological information, we chosen this set of parameters of prism. We used already geology. Then we performed calculation and got curve slightly outside of this strip. Then I changed parameters inside of the program and got new curve, second curve, which is located inside of the strip. This picture is clear because I'm afraid it's not clear. Clear or not? Clear, good. Then what to do next? Huh? No. We will come to this point. Maybe.
If your parameters you've chosen, H1, D, D1, etc., don't fit your geology, then you should project the model.
Sorry?
If your parameters there are not geologically realistic,
No,
then the model can't be even.
No, just a second. Maybe I didn't say clearly. Let us go slowly. I don't like this picture. So again, we have results of measurements. That's our strip. Clear? We have only one data. We have curve, but it's not too bad to visualize. It's not curve. It represents strip. Everybody understands what I'm saying, strip? Huh? You understand what? In effect, you have point, but you know you measure with error. Therefore, it could be little above, a little beneath, above, beneath, above, beneath. So you have your strip. Now about geology. Geology tells me I have right to consider my body as a prism. Geology already told me. Even for simplicity, one prism. Well, because only idea is discussed here. Now, how many parameters this prism has? H1, H2, D1, D2, sigma, correct? 5 parameters. So I wrote correctly H1, H2, D1, D2, sigma. Now, having geological information, I assume that H1 equals 10 meters, H2 20 meters, D1 40 meters, D2 50 meters, 100 meters, and sigma equals 2000 kilogram per meter cube. I don't know approximately. That's my first approximation. I did this step. What is the next step? let us call first approximation step number 1. What is the second step? Calculate using this expression, calculate gravitational field based on this assumption. True? So I did calculation, Newton's law. I will write Newton's law. So scenario, not reasonable scenario. I got this curve. Now, what would be step number 3, which each program has? Seismic, gravity, electromagnetics, everywhere. One element is solution of forward problem. That's why I chosen Newton's law, forward problem. Simple case. What is the step number 3? Yes, so algorithm always has device which allows to change these all 5 parameters, correct? And change in such way that it will approach our new curve closer to experimental curve, correct? So change parameters. And we obtain H11, H21, D11, D21, and sigma 1. Understandable what it is? New set of parameters. Now tell me please what we have to do next. Huh? Oh, that's better. So step number 4, again Newton's law, again solution of forward problem. Everybody understands? But now these parameters are put into here, not geological. Now scenario which I already shown, let me show it again. Suppose after change of these parameters we got curve here. You understand what I'm doing? Second curve. And now back to my question. What to do next? You remember what my question? I repeat.
Find the range of parameters that satisfy the error envelope in the data.
Sorry? How, could you?
Try and find the range of each.
Oh. Do we need to change parameters and calculate again using Newton's law? Huh? In order to approach this curve closer to our experimental data or not? My question is, do we need to change again parameters in order to approach our theoretical curves to experimental curve, or don't do it more?
We're already at the limit.
Oh, thank you very much. No, you are absolutely right. We don't need to do anything more from point of approaching. It's finished. That's the difference between the case of uniqueness and what we have in reality, taking into account that we measure very with some error, we inside of this strip don't change more parameters in order to approach your theoretical curves to experimental. That's the limit. Here you have to stop. So you stopped. If it happens that your new curve were outside, you have to repeat again until your experimental, your forward problem will be inside of strip. Everybody understands? Where is now? Now the new situation. So that's our parameters with which we have to start to work. What we have to do? Now completely different direction. Completely different direction. What is the new direction?
Transfer the sensitivity of the model to each parameter.
What does it mean?
See
Find
how
out how much you can vary each parameter without going outside your envelope.
Exactly. So let us start to change this parameter, each parameter, not separately, together, but that's not important from principal point of view, and find range of change of this parameter, each parameter, so that the curve will remain inside of this strip. That's requirement. It must remain inside of the strip. What would happen? We will find for each parameter H1, one range, A1, B1. For H2, A2, B2. For A G1, A3, B3, G2, A4, B4, sigma, A5, B5. So for each parameter, we find range of change so that curve will remain inside of the strip. You can change inside, you must change inside, you have right to change only in such way that curve would remain inside of this strip. Now, very often, do I speak clearly for everybody? Very good. Now, when you look in this part, what is the most typical scenario which we can which usually observe? Not always. Sometimes we're in extremely good shape. Sometimes a little worse. So when you will get range of change of parameters within which curve remains inside of the strip, what is the scenario which we usually
What we want is very little variation in all those parameters.
we want, that's for sure. That we like it very much. But we are helpless. We are helpless. We have to accept what we get. And what we usually get. So, usually we get the following. Usually. Sum of parameters change in a very small range. Sum of parameters change in very wide range. And still curve remains inside of this strip. What does it mean? Parameter, for example, depth to the bottom could change 1,000 times, but field remains the same. It means you cannot define this parameter. So in mathematics there is term which characterizes problems, inverse problems, when even one parameter cannot be determined. How this? Oh, what? I think I heard the right name. Inverse if even one parameter cannot be determined, this inverse problem is called the ill-pole problem. Ill-pole problem. In general, all geophysical problems don't make one method good, another bad, because there is a wrong impression. Gravity is bad, seismic is good. No, or in seismic, in magnetics, in gravity, in electromagnetics, all solution of inverse problem in general, there are very favorable models when everything is great, called ill-posed problem. Ill, sick. So, this fact does not have relation at all uniqueness, non-uniqueness. So, my first goal is achieved. I have suggestion, please forget about uniqueness, non-uniqueness. It does not have any relation to us because we don't measure, unfortunately, exactly. We have geological noise, man-made noise, instrumental noise, service noise, and this what defines this strip. And for this reason, all our problem ill-pole problem. Now, when we produce this procedure, we in effect produce classification of parameters. Those parameters which change slightly and already cause change of the field, we consider them good parameters. Means we can determine them. Parameters which can change widely, don't affect our field. We say parameters which we cannot define. When we throw away second type parameters, what do we do? Because what my goal is not to give you a lecture about uniqueness, non-uniqueness, but be aware about terminology, nothing else. First of all, I hope we achieved good goal. We threw away uniqueness. We don't need to discuss this question. It does not have relation to us. So please don't tell anybody gravity is not unique, or seismic unique. It's unfair. So, first of all, how procedure of throwing away parameters which cannot be determined, how it's called in mathematics? It's called regularization. Regularization. Then, what is left in reality? It's left group of parameters which change of which makes strong influence on the field, and we obtain, instead of real model, due to regularization, new model. For instance, if we cannot define depth, we obtain, instead of prism, infinite long pipe. New model. And now, if it's only this parameter cannot be determined, but rest could be determined, then this problem is called well-posed problem. So, from ill-posed problem, we travel to well-posed problem, and each proper algorithm which separates parameters in two groups produces regularization. For instance, what does it mean practically mean? We have to be modest if we say this prism cannot be determined. We can determine new model. And one parameter is not real. It's a new completely model of the medium. Now, if we cannot define H1, H2, but can define product surface times density, we again produce regularization and we obtain new model, which is a line. That's all what we can determine. Exactly the same situation, an electrical and electromagnetic method. So when yesterday Danton, for instance, shown you example of different curves, different parameters, in effect he performed regularization and shown which parameter can be determined, which cannot be determined. So that's all what I want you to tell. Maybe that's all. Yes, that's all. Or 1 hour more. We'll let this discuss.
And a lot of things that I thought I did understand, which was a problem, but you've also explained them to me, and it's taken away my fear of the, which has been an underlying problem with me, the fear of the mathematics, which has been very good. I don't have to be frightened of the maths, which is good. You explained the physics well. Possibly we could have looked at a few, or worked a few examples ourselves, as you do in a classic workshop. Unfortunately, that takes a very long time to, for everybody to go through and pencil their own things. But that sometimes makes, it helps cement ideas in the mind if you actually work an example. But if we can all go away and do that now, or try to do it, to concrete it later on next week or in the near future, to get full benefit of the course, of the workshop.
Any other comments about any aspect we really looked at in the last 5.5 days? Wasn't too wide range. Should we have just stuck with some of the more fundamental physics? Should we not have started to show up, especially to the students, or acronyms like BCS, AMT, instead?
As very much of it, a lot of it was the obviously having a reference point to understand what's being talked about. So I think it's still very useful in giving information, and then hopefully when I get out and use it, I'll be able to remember it on a better basis. But certainly can't keep it all up for every moment and just at a certain moment.
I think like one of the from the students' perspective, our education here is obviously a lot less than they do in a lot of European countries. And I think one thing we don't get shown here is limitations of them. We covered MT, CFA, methods, and we didn't get it as right. But basically, I would have gone out into the workforce and thinking, here we go, we're going to do this. But I had absolutely no idea of the limitations and the physical measurement of the limitations. So,
I'd say I thoroughly enjoyed Alex's historical perspectives and putting it in in a chronological order, and which was an extra delicacy for me.
It's very good that you invited me now, because very soon I will forget about it.
Set of learning experiences you'd like to go through in terms of knowing more about EM? Suggestions? We know it. Start to go through the book. Sure, Alex is just talking about. I don't know if that was any policy.
This course represents sort of the level we'd like to see graduates coming out in terms of their understanding of EM, beyond that.
No, it's the level before you graduate.
I would like to, you ask what, I also part of the theory, you ask what we would like, I also have some vision. First of all, for these books which I wrote not for engineers, first of all for students. I teach these 3 books, A, B, C, during 2 semesters for undergraduate students and graduate students. undergraduate students of third and fourth level, graduate students when they come. Usually most of them take my course, even they're working in seismic. Because they come from different countries, have different backgrounds, so some of them never heard about geology and geophysics. For example, electronic engineers, then come to geophysics. Some of them were geophysicists. So this course, there are textbooks in my course. Textbooks. I teach 3 hours per week for each course, for undergraduate and graduate students, 2 semesters. So it's 30 weeks. So it's a course around 90 hours, 90, around 100 hours with 3 books. That's small information, but what I wish, I will be happy if somebody from West Australia or East Australia or whole Australia who came to School of Mines, who likes these books, who likes to understand physical principles of the methods, who wants to understand limitation, area of application, who would not be person of one method. It's important to understand all together. Then you becoming intelligent engineer. And who would learn? He came only to take my course, maybe once, maybe twice, and learn and come here and, for example, teach here. Teach here, teach to give knowledge. Other students also to use in companies to understand which method is better for given geoelectrical conditions, which method is worse, why. That's so pleasant. My experience for many, many years gives me great enjoyment to understand different methods. That's very pleasant. Did I say clearly? Good. And also not afraid applied mathematics. It's reasonable to know how to use it. Not that it must not be self-purpose. No, it's a tool. It's a tool as physics, mathematics. But if you decide to work in geophysics, main goal is application of geophysics for solution practical problems. If you are in exploration, if you are in global, then global. But it's important to understand physics and mathematics, which is only for our purpose, not different areas. No way to become great mathematicians working in geophysics. That's what I think. That's how I. If somebody wants to come, be hired. Don't wait too long.
Okay, if there's no other comments, then I guess the final thing to do here is really to thank Alex for his outstanding contribution in the last 5.5 days, for all the preparation, the months of preparation that I know has gone on to prepare himself for giving such a presentation. I don't know of anyone else who could have done this, or who even would have wanted to front up. And I think really you've been exposed to a very unique level of teaching. I was lucky enough to be involved and exposed to this level of teaching about 5 or 6 years ago now. And I really, once having been exposed to it, like I said on Monday, I thought that I'd like to expose other people to it. And really, I've not been disappointed in the last 5.5 days. I sat up the back not to take notes on people, to see who's been going to sleep. But I have noticed a few people. I mentioned names, but it was only very briefly.
I also enjoy very much with all of you, very much. Your faces become very familiar. It's It looks like I know you for a long time already. That's my impression. That's my feeling.
So I'd just like you to just join me, putting your hands together to thank Alex for his outstanding efforts here in the last 5.5 days. I really do hope, and I know Alex does hope, that you've got a lot out of it, and that you will continue to get information and learning out of this series of presentations. That there is going to be some videos that will be distributed to the universities and also to Western mining libraries. And I'd urge you to go have a look at some of those videos. Each of the different sessions, each 2-hour session is a separate video, so you can go into selected parts, go back over them. And I think if you could just join me in thanking Alex by putting your hands together.
Thank you.
Just have one small gift for you, Alex.
Thank you. Thank you very much.
Just an appreciation of everything.
Can I open later?
You can open later.
Thank you. Thank you.